Imagine sending $1 million to a total stranger across the globe at 2 in the morning on a Sunday.
Right.
No bank approves it. No company processes it. I mean, no one is asking for your name or your zip code or, your mother's maiden name.
And none of that.
And yet, within minutes, both you and the recipient know with absolute, mathematical certainty that the transfer is irreversible.
Yeah, which is just wild to think about.
It is. And until relatively recently, that scenario was completely impossible in the digital world. But today, we are cracking open the exact mechanics of how that impossible scenario actually became a reality.
Welcome to the deep dive.
Exactly. And look, we're skipping the hype today. We're skipping the market charts, the volatile prices, the endless talking heads on TV. None of that is happening here.
Right. Our mission today is purely mechanical.
Purely mechanical. We are going to look under the hood and explain exactly how the math, the algorithm, and the network actually function. And we're doing it using nothing but the raw foundational source material for this entire revolution.
It's a white paper.
Yes. The 2008 9-page white paper titled Bitcoin, a peer-to-peer electronic cash system, written by the pseudonymous Satoshi Nakamoto.
And, it remains just a remarkably elegant document. If you read it today, the brevity is what really stands out.
9 pages.
Right. I mean, you might expect the foundation of a decentralized global financial network to be this dense, impenetrable textbook of legal code and economic theory, but it's just 9 pages.
Yeah.
And the reason it's so concise is that it isn't fundamentally a paper about money. At its core, it's a proposed solution to a profound, decades-old computer science problem.
Which is, how do you achieve consensus, right?
Exactly. How do you achieve absolute consensus among a massive, scattered group of anonymous strangers without ever appointing a central authority to tell them what the truth is?
Okay, let's unpack this,
Right.
because that is a massive paradigm shift. But to understand the solution, we have to really deeply understand the problem Satoshi was pointing at.
Yeah, the baseline.
Right. In the very introduction of the white paper, there's this heavy, almost philosophical critique of what the text calls the trust-based model of traditional commerce.
The whole system we use every day.
Yeah, if I buy something online right now, I'm using that trust-based model. So what exactly is the white paper arguing is so fundamentally broken about it?
Well, the critique really centers on our total reliance on financial institutions. Banks, credit card networks, payment processors.
The middlemen.
Right. When you buy a pair of shoes online, you and the shoe merchant are not actually exchanging value with each other. You are both communicating with a trusted third party.
The bank sits right in the middle.
The bank sits in the middle. You ask the bank to debit your account. The merchant asks the bank to credit theirs. And you both completely trust the bank's internal ledger to reflect reality.
Which, mostly works, right?
The paper actually concedes that. For the most part, it works well enough for daily life. But the underlying architecture suffers from an inherent, inescapable weakness.
Because that trusted third party has to act as a referee.
Precisely. The white paper states that in this trust-based model, completely non-reversible transactions are not actually possible.
Yeah.
Financial institutions cannot avoid mediating disputes. If a customer complains that the shoes never arrived or that their credit card was stolen, the bank is legally and operationally forced to step in, investigate, and potentially reverse the transaction.
Which, sounds like a good thing for the consumer, right? I want to be able to do a chargeback if I get scammed.
Sure.
But the paper points out the massive hidden cost to this safety net. Being a referee is incredibly expensive.
Oh, massively.
The bank has to employ armies of customer service reps, fraud investigators, compliance officers, lawyers. All of that overhead has to be paid for somehow.
And it gets paid for through transaction costs.
Yeah.
The bank takes a cut of every single purchase.
And by imposing those transaction costs, the white paper argues we fundamentally alter the landscape of what is economically possible. The text specifically highlights that the cost of mediation increases the, and this is a quote, minimum practical transaction size. This completely cuts off the possibility of small, casual, digital transactions.
We see this all the time.
Exactly. This is why a digital newspaper cannot charge me 3 cents to read a single article. If the payment processor charges a 30-cent flat fee plus a percentage on every transaction, a 3-cent purchase literally costs the business money to process.
The mediation cost completely swallows the transaction. It dictates the business models of the entire internet.
Yeah.
But the fallout of reversibility goes even deeper than just transaction fees. The paper notes that because payments can be reversed, the need for trust spreads like a contagion through the entire system.
What do you mean by contagion?
Well, merchants have to be inherently suspicious of their own customers. If a merchant provides a digital service, say a software download, and the customer consumes it immediately but then successfully executes a chargeback with their bank, the merchant is simply out of luck.
Because you can't return a downloaded file.
Right. The service cannot be returned.
Oh, this actually explains a line in the paper that really caught my eye. Satoshi writes that merchants end up hassling customers for more information than they would otherwise need.
Yes.
Like, if I am buying a $2 digital sticker, the merchant doesn't actually need to know my billing address, my zip code, or my phone number to deliver a digital file.
They don't care where you live.
No, they demand all that data so they have a paper trail to show the referee, the bank, in case I try to commit fraud and reverse the charge.
Exactly. The system forces merchants into the business of data collection and risk management. And even with all that friction in data collection, the white paper bluntly states that a certain percentage of fraud is accepted as unavoidable.
Wow.
Yeah, the banks know they can't catch it all. The merchants know they will lose a certain amount of revenue to chargebacks. So society just bakes the cost of that unavoidable fraud into the price of everything we buy.
It's just an accepted inefficiency.
Right.
But the paper points out that this inefficiency doesn't exist in the physical world. Like, if I walk into a coffee shop and hand the barista a physical $5 bill, there is no trusted third party mediating that exchange.
No bank there.
Exactly. The barista has the physical paper, and I don't. The transaction is physically, practically irreversible. The barista doesn't ask for my phone number or my zip code because they don't need to worry about a chargeback.
But translating that physical interaction to the digital realm, that was the great unsolved problem of cryptography prior to 2008.
How do you hand someone a digital $5 bill over a communications channel with no bank in the middle and ensure it cannot be reversed?
That's the million-dollar question.
Okay, so we've eliminated the bank. We are removing the central referee. But wait, if we are just sending digital files back and forth, how on earth do we prove who owns what? Like, how do I prove to the merchant that I actually have the digital money to send them in the first place? The paper transitions here to define what an electronic coin actually is, and the definition is wonderfully counterintuitive.
It says an electronic coin is simply a chain of digital signatures.
A chain of signatures.
This is a profound conceptual leap. You really have to discard the idea of a digital coin as a static computer file sitting on a hard drive, like an MP3 or a JPEG.
So it's not a file in a folder.
No, in Satoshi's architecture, the coin is its history. The entire identity of the asset is just a recorded lineage of ownership.
To understand how that works, I think we need to quickly touch on how digital signatures function in cryptography, specifically public and private keys, because the paper leans on this heavily.
Absolutely. A good way to visualize it is to imagine every user has two things: a public key, which acts like a mailbox with a slot in it, and a private key, which is the physical key that opens that mailbox.
Okay, I'm with you.
You can give your public key your mailbox address to anyone in the world. Anyone can drop a message or a payment through the slot. But only you, holding the private key, can open the box and access what's inside.
Makes sense.
Furthermore, you can use your private key to digitally sign a message. When you do, anyone looking at your public key can verify, using complex mathematics, that the signature could only have been created by the person holding the corresponding private key.
So it proves authorization without ever revealing the private key itself.
Exactly.
So applying that to the white paper's definition of a coin, how does a transaction actually happen?
Well, according to the text, each owner transfers the coin to the next person by digitally signing two pieces of information: a cryptographic hash of the previous transaction and the public key of the next owner.
Okay.
These two pieces of data, along with the signature, are essentially appended to the end of the coin's history.
I want to make sure we are really visualizing this for you, the listener. Imagine that physical $5 bill again. But imagine that every single time it changes hands, you are required to write a cryptographically secure receipt that says, I, holding private key A, am transferring the value from my previous transaction to the person holding public key B.
Right.
You staple that receipt to the physical bill. Then, when person B wants to spend it, they write a new receipt, sign it with private key D, transferring it to public key C, and staple that to the bill.
And it just keeps going.
Over time, you build this massive trailing tail of receipts stapled to the money. If a payee ever wants to verify that the coin is valid, they don't ask a bank. They just read the receipts.
They can cryptographically verify every single signature all the way back to the moment the coin was created.
That is the exact mechanism. The payee can verify the signatures to verify the chain of ownership. It completely solves the problem of authorization. You can mathematically prove that the person sending you the funds is the authorized owner of those funds.
But hold on. This seems like it leaves a massive, glaring loophole.
Oh,
If this is all just digital data, just a string of signatures and hashes, what is stopping me from simply copying that exact file?
the classic digital problem.
Right. I could take my perfect cryptographically verified chain of signatures, hit CTRL plus C, and send that exact same file to a car dealership to buy a car, and simultaneously email it to a real estate agent to buy a house.
Yeah, you authorized both.
I hold the private key. Both recipients look at the chain and see a valid history.
You have just articulated the core villain of the entire white paper, the primary obstacle of early digital cash, the double spending problem.
It's the biggest hurdle.
As you noted, in the physical world, the laws of physics prevent double spending. You cannot physically hand the same $5 bill to two different cashiers at the exact same time. But digital information is entirely unconstrained by physics.
It is designed, by its very nature, to be duplicated perfectly and infinitely.
So if anyone can copy the file, how did people try to solve this before 2008?
The paper actually discusses the traditional solution, which relies once again on a trusted central authority, the mint model.
A mint.
In this model, to prevent double spending, a central mint acts as the clearinghouse for every single transaction. After every transaction, the digital coin essentially has to be returned to the mint.
So the mint takes it back.
The mint destroys it, verifies it hasn't been spent before, and then issues a brand new digital coin to the new owner. In this system, the only coins that are trusted are the ones issued directly by the mint.
Which drags us right back to the exact problem we were trying to escape in the introduction.
Exactly.
If the mint has to verify every transaction, we are back to a trust-based model with a central referee.
Yes, and the white paper outlines the fatal flaw of the mint model. The fate of the entire monetary system depends entirely on the company running the mint. Every single transaction must be routed through them, exactly like a modern bank.
It creates a massive single point of failure.
Huge. If the mint's servers go down, the global economy halts. If the mint's database is corrupted, ownership is lost. If the mint decides they don't like a specific user, they can censor their transactions.
So Satoshi sets an incredibly strict requirement here. We need a way for the merchant receiving the money to know with absolute mathematical certainty that the previous owner did not sign any earlier transactions.
Right.
As the text explicitly states, for our purposes, the earliest transaction is the only one that counts. We do not care about later attempts to double spend.
First come, first served.
Exactly. If you try to buy the car and the house at the same time, the first transaction to hit the system is the valid one. The second one is rejected as fraud.
But confirming which transaction was first is the crux of the problem. How do you prove the absence of something? How do you prove to the car dealer that you didn't quietly send those funds to the real estate agent 10 minutes ago?
That's tough.
The paper establishes a fundamental truth here. The only way to confirm the absence of a previous transaction is to be aware of all transactions.
The mint knew about all transactions because everything went through their central server. Without a central server, how does everyone know everything?
The paper proposes a radical pivot. It states that to accomplish this without a trusted third party, transactions must be publicly announced.
Publicly announced.
The network cannot be hidden. Every time someone wants to transfer value, they must shout it to the entire network. And furthermore, we need a system for all participants to agree on a single history of the order in which those transactions were received.
A single, universally agreed upon history. That is the magic trick. The payee needs cryptographic proof that at the time of their transaction, the majority of the global network agreed it was the first one received.
Right.
But how do you get thousands of scattered anonymous computers around the world to agree on the exact time and sequence of events, especially when you consider network latency?
You can't.
You can't just rely on the internal clock of a computer in Tokyo and a computer in New York, because internal clocks can be spoofed or out of sync. We need a decentralized way to prove time.
Which introduces the first major mechanical innovation in the paper, the timestamp server.
And the text describes this timestamp server in a way that is totally different from what we usually think of as a timestamp. Normally, when I save a file on my computer, the operating system just slaps the current date and time onto the file metadata.
Right, like Tuesday at 4 p.m.
But the paper's timestamp server is an entirely different beast.
It really is. The paper states that the timestamp server works by taking a block of items, in our case, a batch of these publicly announced transactions, hashing them together, and then widely publishing the hash.
Okay, we used the term hash earlier when talking about signatures, but we need to stop and deeply explore what a hash function is because the entire architecture of the system rests on it.
It does.
The text specifically mentions a hashing algorithm called SHA-256. How does a mathematical hash actually work?
Think of a hash function as a one-way mathematical meat grinder. You can feed any amount of digital data into this grinder. You could feed it a single word, like apple. You could feed it a list of 10,000 financial transactions. You could feed it the entire text of the Encyclopedia Britannica. No matter how much data you put in, when you turn the crank, the output is always a fixed-length string of characters.
So it standardizes the size.
Yes. For SHA-256, it's a 256-bit number, usually represented as a 64-character hexadecimal string of letters and numbers. It looks like complete and utter gibberish.
But it's not random gibberish. That's the key.
Precisely, it is entirely deterministic. If you put the exact same Encyclopedia Britannica into the meat grinder tomorrow, you will get the exact same 64-character string of gibberish out the other side.
Wow.
However, the magic of the hash function is its extreme sensitivity, often called the avalanche effect. If you go into the Encyclopedia Britannica and change one single comma on page 4000 and run the whole thing through the meat grinder again, the output hash will change completely and unpredictably.
So it's not just off by one letter.
No, it won't just change by one letter. The entire 64-character string will look totally different from the first one.
And crucially, it's a one-way street. You cannot look at the 64-character hash and somehow reverse engineer it to figure out that the input was the Encyclopedia Britannica.
Impossible.
It only goes one direction. So applying this to the white paper, by publishing the hash of a block of transactions, the timestamp server proves that those specific transactions must have existed at that specific moment in time.
Yes. They obviously had to exist in that exact configuration in order to be fed into the hash function to produce that specific output.
Right.
The paper notes that to prove this, you could theoretically publish this hash in a widely distributed place, like a newspaper or a Usenet post. Once the hash is printed in the newspaper, it proves the data existed before the newspaper was printed.
It's like those kidnapping movies where they make the hostage hold up today's front page of the New York Times to prove they are still alive today.
It is the exact same cryptographic concept, but automated.
That's fascinating.
But a single timestamp is just a moment in isolation. What makes this a robust server is how the text links these timestamps together. The white paper states that each timestamp must include the previous timestamp in its hash.
Hold on. Let me trace the logic here. If the hash changes every time the input data changes, and I take the 64-character hash from yesterday's block of transactions, and I include it as part of the input data for today's block of transactions, then today's hash is mathematically derived from yesterday's hash.
Yes, they form a continuous, unbroken chain.
And because of the avalanche effect, if an attacker wants to go back and alter a transaction from a week ago, say, to erase a payment they made, they would have to change the data in that old block.
Right.
But changing the data changes that block's hash. And because that old hash was inside the next block's hash changes, which changes the next one and the next one.
It cascades.
It causes a mathematical avalanche that completely invalidates every single block that came after it.
It creates a mathematically sealed history. Any attempt to alter the past loudly breaks the present.
That's brilliant.
But there is still a missing piece here. Publishing a hash in a newspaper or on a message board requires a central publisher. It requires a human being or a central server to collect the transactions, hash them, and print them.
Right, which we don't want.
Exactly. How do we automate this distributed timestamp server on a peer-to-peer basis where no single computer is in charge of publishing the truth?
Which brings us to the engine room of the white paper. The most famous and perhaps most misunderstood mechanism in the entire document, proof of work.
Proof of work.
This is how you teach a decentralized algorithm to reach consensus without a leader.
To implement a distributed timestamp server on a peer-to-peer basis, the paper states we will need to use a proof-of-work system similar to Adam Back's Hashcash.
Hashcash.
Now, Hashcash was originally invented in the late 1990s to combat email spam. The idea was to force a sender's computer to do a tiny bit of computationally expensive math before sending an email.
So it slows them down.
It was trivial for a normal user sending one email, but it made it economically unviable for a spammer trying to send 1 million emails a minute. Satoshi repurposed this concept not for spam, but for consensus.
Let's walk through the actual math of this proof of work because it's brilliant in its brutality.
It really is.
The text says the proof of work involves scanning for a specific value when hashing the block. What are we scanning for?
Remember that our hash function, SHA-25B6, spits out a 64-character string that looks entirely random. The proof of work protocol dictates that the network will only accept a block of transactions as valid if the hash of that block begins with a certain number of 0 bits.
Meaning the output has to look something like 00000000000, followed by the rest of the random gibberish.
Correct, but here is the critical problem. Because the hash function is unpredictable, you cannot just tell the meat grinder to give you an output starting with 10 zeros.
You just get what you get.
You have your block of transactions, and if you hash them, you get whatever hash you get. If it doesn't start with 10 zeros, you can't just change the transactions to try again, because that would alter the financial history you were trying to record.
So if you can't change the transactions and you can't predict the hash, how do you ever find a hash with enough leading zeros?
The paper explains that you implement proof of work by introducing a nonce into the block.
A nonce, a number used once. This is basically just a blank space in the block, a dummy variable, where the computer is allowed to plug in any random number it wants.
Exactly. The process goes like this. The computer takes the block of transactions, the hash of the previous block, and adds a nonce of 1. It hashes the whole package.
Okay.
Does the resulting hash start with the required number of zeros? No. So it changes the nonce to 2. It hashes again. Does it start with enough zeros? No. It changes the nonce to 3.
It just keeps going.
The text states the computer must increment this nonce endlessly until a value is found that gives the block's hash the required 0 bits.
I always picture this like a massive global combination lock. But it's a lock with billions of independent dials, and you cannot use logic or lock-picking skills to open it.
Nope, pure luck.
You simply have to spin the dials blindly, guess a combination, check if it opens, and if it doesn't, spin again. And these computers are doing this millions or billions of times every single second. It is pure brute force guessing.
Yes.
But when you look at that from the outside, isn't it an incredibly inefficient system? Like, why require computers to burn massive amounts of electricity just blindly guessing random numbers?
Because the inefficiency isn't a bug, it is the fundamental security feature of the network.
Oh, really?
Yeah. The text explicitly points out that the average work required is exponential to the number of 0 bits required. To understand why, think about hexadecimal outputs. If you need the hash to start with just one specific character, say 0, you have a 1 in 16 chance of finding it on any given guess.
Okay, simple enough.
But if the network requires 2 leading zeros, the odds aren't just doubled, they increase exponentially to 1 in 256. 3 leading zeros is 1 in 4,096.
Wow, it ramps up fast.
By requiring dozens of leading zeros, the network ensures that finding that winning nonce takes an immense, physically measurable amount of CPU power and electricity.
It is mathematically guaranteed to be incredibly difficult to find. But here is the genius counterbalance that the paper highlights. While it takes an ocean of electricity and billions of guesses to find the winning nonce, once you find it and announce it to the network, anyone else can verify it instantly.
That asymmetry is everything.
Right.
It might take you 10 trillion guesses to find the right combination, but once you broadcast the nonces, say 42,489, I can just plug that number into my block, run it through the SHA-256 meat grinder exactly one time, see the leading zeros, and immediately agree with you.
Verification takes a fraction of a millisecond. And the paper uses this required physical effort to lock the history into place. The text states that once the CPU effort has been expended to satisfy the proof of work, the block cannot be changed without redoing the work.
And remember the chain of hashes we discussed, the avalanche effect.
Yeah.
If an attacker wants to rewrite a transaction from yesterday, they don't just have to solve the massive mathematical puzzle for yesterday's block all over again, because all subsequent blocks are chained to it. Changing yesterday's block invalidates today's block.
Oh, man.
The attacker would have to redo the proof of work for the altered block and simultaneously redo the proof of work for every single block that was chained after it, all while the rest of the honest network is relentlessly moving forward, adding new blocks.
It is a cryptographic treadmill that a minority attacker can theoretically never catch up on.
Precisely. By anchoring the digital history to the physical expenditure of electricity, Satoshi solves a huge flaw in decentralized networks.
The voting problem.
The paper explicitly addresses the majority decision problem. If you have a network with no leader, who gets to vote on which history is true? The text notes that if voting was based on one IP address, one vote, the system would be hopelessly vulnerable.
It would be trivial to subvert. A bad actor could just use a botnet or rent server space to spin up 1 million fake IP addresses and instantly outvote everyone else in the network.
It's called a Sybil attack. IP addresses are cheap and frictionless to create.
But proof of work entirely shifts the paradigm. The paper declares that proof of work is essentially one CPU, one vote.
You cannot fake computational power. You cannot spoof electricity. You either actually expended the physical energy required to find the winning nonce or you didn't.
Right.
Therefore, the majority decision of the network is always represented by the longest chain, because the longest chain mathematically proves that the greatest amount of proof of work effort was invested in building it.
The longest chain is the truth because it has the most physical energy backing it up. But the paper also anticipates a practical issue with this. Technology doesn't stand still. According to Moore's law, computers get faster and more efficient every year.
They do.
If the math puzzle stays the same, but the computers get 10 times faster, they're going to guess the combinations 10 times quicker. Blocks would be found too fast, and the network would become unstable.
The white paper addresses this with a self-regulating mechanism, dynamic difficulty adjustment.
That's dynamic difficulty.
To compensate for increasing hardware speeds and varying interest in running nodes over time, the algorithm automatically adjusts the proof of work difficulty. It calculates a moving average to target a very specific, steady rate of block generation, say, 1 block every 10 minutes.
Okay.
If the network suddenly sees a massive influx of new CPU power and blocks start being solved every 5 minutes, the algorithm automatically reacts. It requires more leading 0 bits.
It demands an exponentially harder puzzle.
Exactly. The difficulty goes up, slowing the network back down to the target rate. Conversely, if a bunch of computers leave the network and blocks are taking 20 minutes to find, the algorithm requires fewer 0 bits.
The puzzle gets easier.
The puzzle gets easier. The system is constantly algorithmically seeking equilibrium, regardless of how much hardware is thrown at it.
So we have the cryptographic signatures proving ownership, we have the timestamp chain preventing alteration, and we have proof of work making consensus of physical reality.
The core pillars.
The paper then takes all these gears and puts them together into the actual network rules. It spells out, step by step, the loop that these nodes the computers running the software actually execute.
It breaks it down into a remarkably simple 6-step operational loop.
Let's hear it.
Step 1. New transactions are broadcast to all nodes. Users announce they want to move funds. Step 2. Each node independently collects these new transactions into a block.
Making a batch.
Step 3. Each node begins working on finding the difficult proof of work for its specific block. They start spinning the dials, incrementing the nonce.
Burning electricity, racing each other.
Step 4. When a node finally finds a winning in proof of work, it immediately broadcasts its solved block to all the other nodes.
Done.
Step 5. The receiving nodes do not blindly accept it. They accept the block only if all transactions inside it are valid and not already spent. They check the digital signatures, and they verify against the history to ensure no double spending occurred.
And step 6. Nodes express their acceptance of the block by immediately moving on to create the next block in the chain. And crucially, they use the hash of the accepted block as the previous hash for their new block.
They essentially vote yes on the new block by building on top of it.
That is the complete cycle of consensus.
It is.
But there is a massive logistical question here that the paper tackles, and it's a scenario that really tests the resilience of the network. What happens in the event of a tie?
Ah, the tiebreaker.
Imagine Node A is in Tokyo and Node B is in New York. They've both collected transactions, they're both spinning their nonces, and by sheer mathematical coincidence, they both find a winning proof of work at the exact same millisecond.
Right.
They both broadcast their perfectly valid but slightly different blocks to the network. Who wins? You can't have two conflicting histories.
In a decentralized global network with varying latency, this isn't just a hypothetical, it's an inevitability.
It's going to happen.
The paper provides a beautifully elegant rule for breaking these ties. Nodes always consider the longest chain to be the correct one.
But wait, if they broadcast at the exact same time, the chains are the exact same length. Tokyo's chain is block 100, and New York's chain is block 100.
Correct. So what happens is a temporary network split. Because of geography, the nodes in Asia will likely receive Tokyo's block 100 first. The nodes in North America will receive New York's block 100 first.
Okay, that makes sense.
The rule states that a node will work on the first valid block it receives. So the Asian nodes start building block 101 on top of the Tokyo block. The American nodes start building block 101 on top of the New York block.
The network is literally working on two different realities.
Yes, but only temporarily. The paper notes that nodes save the alternate branch they received, just in case it becomes longer later. The tie is entirely broken when the next proof of work is found.
Oh, I see.
Let's say a computer in Europe, which was building on the Tokyo branch, solves the puzzle for block 101 first. They broadcast block 101. Now, the Tokyo branch is mathematically longer than the New York branch.
It has more accumulated proof of work.
Exactly. The moment that block 101 propagates across the globe, all the nodes in North America that were working on the New York branch immediately see that their branch is shorter.
They realize they're behind.
The algorithm dictates they instantly drop the New York branch, abandon their current work, and switch over to the Tokyo branch. The New York block becomes what's called an orphaned block, completely discarded.
The entire network converges back into a single unified history based purely on the math of the longest chain.
It's like a self-healing organism. It doesn't need a referee to declare a winner. The math resolves the conflict organically.
And the paper points out that this unstructured simplicity makes the network incredibly robust against failure. The text explicitly says that messages are broadcast on a best effort basis. Transactions don't have to reach every single node perfectly to succeed.
Right. As long as they reach many nodes, they'll get bundled into a block before long.
This tolerance for dropped connections is vital. Nodes can simply drop off the network entirely, go to sleep, and rejoin at will.
Because when a node boots back up, how does it know what happened while it was offline? It doesn't need to ask a trusted server.
It just checks the math.
It simply queries its peers for the longest proof of work chain, cryptographically verifies the hashes itself, accepts that longest chain as the absolute proof of what happened while it was gone, and starts working from the new tip of the chain.
So the mechanics of the engine are incredibly solid. But the white paper recognizes a fundamentally human problem. We just established that finding this proof of work requires a massive expenditure of CPU time, hardware, and electricity.
It's not cheap.
All of that costs real money. Why on earth would anyone voluntarily donate their computer power to maintain this decentralized network? What is the carrot?
The carrot is the incentive structure.
Okay, let's talk incentives.
The white paper states that, by convention, the first transaction in a block is a special transaction that starts a brand new coin owned by the creator of the block.
So the node that successfully solves the proof of work puzzle, the one that wins the race, gets to mint new money out of thin air and pay it to themselves.
Yes, it's called the Coinbase transaction. This elegant mechanism serves two absolutely vital purposes simultaneously. First, it provides the necessary economic incentive for nodes to support the network, validating transactions and securing the chain.
Right.
Second, it solves the distribution problem. Since there is no central bank to print currency and issue it to the public, there has to be a mechanism to initially distribute coins into circulation.
And Satoshi uses a very deliberate analogy in the text here. They compare the steady addition of new coins to gold miners.
Gold miners, yeah.
Gold miners expend physical resources, heavy machinery, human labor, time to extract gold from the earth and add it to circulation. In this digital system, it is CPU time and electricity that are expended to add digital coins to circulation.
It ties the creation of digital value directly to the consumption of physical energy.
It's a very fitting economic parallel. But the paper also introduces the secondary incentive mechanism transaction fees.
Ah, the fees.
A user sending a payment has the option to make the output value of their transaction slightly less than the input value. For example, if they have a 10-coin input, they might send 9.9 coins to the merchant. That 0.1 coin difference is a transaction fee.
And where does that fee go?
It is added to the incentive value of the block containing the transaction. The miner, who solves the proof of work, gets the newly minted coins, plus all the transaction fees from every transaction included in that block.
And the text makes a critical prediction about the long-term future of this incentive structure. It notes that eventually, Once a predetermined number of coins have entered circulation, the supply will be capped.
The cap.
At that point, the incentive can transition entirely to transaction fees and become completely inflation-free. There will be no more new coins minted. The miners will be sustained purely by the fees attached to the transactions they process.
But the genius of the paper's incentive design isn't just about rewarding participation. The paper makes a compelling game-theoretic argument that the incentive is fundamentally a security feature.
It is designed to encourage nodes to stay honest.
Let me push back on that.
Yeah.
Because human nature tells us that wherever there is money to be made, someone will eventually try to cheat the system. What happens if an incredibly well-funded, greedy attacker manages to assemble more CPU power than all the honest nodes combined? We call it a 51% attack.
Yeah.
If they control the longest chain, couldn't they just overpower the network, rewrite history, and steal everyone's money?
The paper anticipates this exact scenario and directly addresses it. First, we must clarify the limits of such an attack. The paper explicitly states that even if an attacker controls a majority of CPU power, they cannot simply steal other people's money or create coins out of thin air.
Why not?
Because the honest nodes would still instantly reject any transaction that lacks a valid digital signature. The attacker doesn't have your private keys, so they can't authorize a spend from your account.
Right. So what can the attacker do?
The paper states they can only try to change one of their own recent transactions to take back money they just spent. They can execute a double spend.
Okay, so a rollback.
But the text then analyzes the game theory of the attacker's choices. It argues the attacker would face a crossroads between two paths. Path 1 used their massive computational advantage to defraud merchants by rewriting the chain to reverse their own payments.
Doing goods and keeping their money.
Exactly. Path 2 used that same massive computational advantage to simply follow the rules, generate new blocks, and collect the block rewards and transaction fees. Because the attacker has more CPU power than anyone else, they are mathematically guaranteed to win the puzzle more often than anyone else.
And the paper concludes that the rules inherently favor the attacker making more money by playing fairly than by undermining the system.
Yes.
If an attacker with massive resources successfully executes a 51% attack and visibly rewrites the blockchain, they destroy global confidence in the network. If confidence collapses, the value of the currency collapses.
It's self-defeating.
Therefore, the validity of the attacker's own wealth, the coins they hold, and the vast amount of new coins they could be mining legally plummets to zero. It is mutually assured destruction driven entirely by self-interest.
As the text says, they ought to find it more profitable to play by the rules than to undermine the system and the validity of their own wealth.
It aligns greed with security. Now, moving past the incentive structure, Satoshi anticipates a massive practical engineering bottleneck.
Storage?
If this network runs forever, and literally every single transaction globally is recorded on this public ledger, storing a complete history of every coffee ever bought and every invoice ever paid seems computationally impossible.
Hard drives will eventually fill up.
The text addresses this head-on with a section called Reclaiming Disk Space. How do they solve the storage problem without losing the history?
The paper proposes that once the latest transaction in a coin is buried under enough blocks, the spent transactions before it can be safely discarded to save disk space. But as we discussed with the avalanche effect, you cannot just randomly delete old data. If you delete a transaction, you change the block's hash. If the block's hash changes, the chain breaks.
So how do you delete data without breaking the cryptographic seal?
To facilitate this, the text explains that the transactions within a block are not just hashed together in one giant clump. They are hashed in a very specific cryptographic structure called a Merkle tree.
Okay, let's visualize a Merkle tree for the listener, because the name sounds intimidating, but the concept is brilliant.
Go for it.
Imagine a massive tennis tournament bracket, like Wimbledon. At the very bottom, you have all the individual matches. These are the individual transactions. When two players play, the winner advances to the next bracket.
Right.
In a Merkle tree, you pair up two transactions, hash them together, and the resulting hash advances to the next level. Then you pair that branch with another branch, hash them together, and move up again. You keep combining and hashing all the way up the tournament bracket until you are left with only one single final hash at the very top. That absolute top hash is called the Merkle root.
That tournament bracket analogy is perfect. And here is the crucial engineering trick. Only that final Merkle root is included in the block's header. The interior hashes, the intermediate branches, and the raw transaction data at the bottom do not need to be stored in the main block header.
So how does this save space?
Because if a transaction is deeply buried and spent, the software can compact the block by stubbing off the branches of the Merkle tree that contain that spent transaction.
Oh, I see.
Imagine erasing the early round scores from the tennis bracket, but keeping the path that shows the eventual winner. You can delete the heavy raw data of the old transactions, but because you keep the intermediate hashes, the final Merkle root at the top remains mathematically identical.
That's incredibly clever.
The cryptographic chain connecting the blocks is completely unbroken, even though the underlying data was deleted.
And Satoshi provides the specific math to prove this is viable.
Mm,
Reading these numbers from the 2008 text is like looking at a technological time capsule.
it really is.
They calculate that a block header containing only the Merkle root and the proof of work data is about 80 bytes. If blocks are generated every 10 minutes, that is 80 bytes times 6 blocks an hour times 24 hours times 365 days, which comes out to roughly 4.2 megabytes of growth per year.
4.2 megabytes.
The text then notes that computer systems typically sell with 2 gigabytes of RAM as of 2008 and cites Moore's law predicting growth of 1.2 gigabytes per year. Satoshi concludes that storage should not be a problem, even if the block headers must be kept entirely in memory. 4.2 megabytes a year is nothing.
And that tiny 4.2 megabyte footprint leads directly into another critical feature detailed in the white paper, Simplified Payment Verification, or SPV.
SPV.
This is essential for the listener to understand because it explains how ordinary people using regular devices can actually interact with this massive cryptographic network. The paper states it is possible to verify payments without running a full heavy network node.
Right, because if I'm running a small coffee shop or just using an app on my phone, I don't want to dedicate a massive server farm to download the entire multi-gigabyte history of every transaction ever made just to verify a $5 coffee purchase.
And you don't have to. A user utilizing SPV only needs to keep a copy of the block headers of the longest proof of work chain. They can get these headers by simply querying network nodes until they are convinced they have the longest chain.
So just the headers?
When a customer sends them a payment, the SPV user doesn't verify the transaction against the entire ledger. Instead, they obtain the specific Merkle branch, the specific path through the tournament bracket that links their incoming transaction to the block it was timestamped in.
They just trace their specific leaf up the branch to see that it matches the root in the header.
Exactly. Now, the text makes a very clear, honest distinction here about the limits of this method. As an SPV user, you cannot check the transaction for yourself. You don't have the ledger to independently verify if that coin was double spent somewhere else in the past.
Right, you're relying on the network.
However, by linking it to a place in the proof of work chain, you can see that a full network node has accepted it. And as more blocks are added after it, that further confirms the network has accepted it as valid.
But Satoshi explicitly notes a vulnerability here. The text states that SPV is reliable as long as honest nodes control the network. But it is vulnerable if the network is overpowered by an attacker.
Yes. While full network nodes can independently verify every single transaction against the entire history and cannot be tricked into accepting a fake payment, the simplified SPV method relies on the consensus of others.
It's very tough.
It can be fooled by an attacker's fabricated transactions, at least for as long as the attacker can sustain overpowering the network.
So what is the defense? How does the coffee shop protect itself?
The paper suggests a strategy where SPV users accept alerts from full network nodes. If a full node detects an invalid block being propagated by an attacker, it sends an alert across the network.
An alarm bell.
This alert prompts the user's SPV software to temporarily download the full block and investigate the inconsistency itself. Furthermore, the text gives a very practical warning. Businesses receiving frequent or large payments will probably still want to run their own full nodes for independent security and quicker verification.
That makes total sense.
Yeah.
SPV is incredibly useful for the casual mobile user, but full nodes remain the backbone of truth for serious commerce.
Absolutely.
We should also briefly mention a neat mechanical note the paper touches on regarding combining and splitting value. It points out that it would be incredibly unwieldy to make a separate, distinct transaction for every single cent in a transfer. So transactions are designed to have multiple inputs and outputs.
It mirrors how physical cash works. If you buy a $3 item with a $10 bill, you don't cut the bill into pieces, you hand over the 10 and you get a 5 and 2 ones back. Digital transactions work similarly. You might have one big input or lots of little inputs combining like pocket change. And there are usually two outputs, one for the actual payment to the merchant, and one returning the remaining change back to the sender's own public key. It is a necessary feature for efficiency.
Okay, let's pivot to privacy, because the paper addresses a seemingly massive contradiction in the design. We established in the very beginning that to prevent double spending without a central mint, every transaction must be publicly announced, a public ledger.
Right.
But in traditional banking, privacy is maintained by doing the exact opposite, by strictly limiting access to information. The bank knows, you know, but the public doesn't. If everything in this new system is broadcast to the world, how on earth can there be any privacy at all?
The white paper acknowledges that the traditional privacy model is completely precluded here. You cannot hide the transactions. But it proposes that privacy can still be maintained by breaking the flow of information in a different place by keeping the public keys themselves anonymous.
The text uses a great analogy here, comparing it to a stock exchange tape.
Yes, on a public stock exchange, the ticker tape broadcasts the time and the size of individual trades to the entire world. Everyone can see that 10,000 shares of Company X were sold at $50 at 10 a.m.
But the tape does not tell you who the parties were.
It doesn't say John Smith sold them to Jane Doe.
So the public ledger shows that someone with public key A sent 5 coins to someone with public key B, but there is no real-world name attached to those keys.
That is the baseline of privacy. However, the white paper recommends a crucial additional firewall. It explicitly states that a new key pair should be used for every single transaction.
Meaning you shouldn't just create one public key and use it like a permanent bank account number for years.
Never.
Because if you do, anyone analyzing the public ledger could see all the activity associated with that one number. If they ever figured out your identity, say, you use that key to buy a pizza sent to your house, they could retroactively see your entire financial history. By generating a brand new anonymous identity for every single transaction, it keeps the transactions from being mathematically linked to a common owner.
But again, the paper is rigorously transparent about the shortcomings of its own design. It notes that some linking is still unavoidable with multi-input transactions.
Like combining your change.
If you want to buy a car and you need to combine 50 small payments you received in the past to afford it, that multi-input transaction necessarily reveals to the public that all those 50 separate inputs are actually owned by the exact same person.
The firewall drops. The network sees that all those pseudonyms are controlled by the same wallet.
Exactly. And the text warns that if the owner of a key is somehow unmasked, this linking could reveal other transactions that belong to the same owner. The system is pseudonymous, not perfectly anonymous. It requires disciplined operational security by the user to maintain privacy.
Okay, take a deep breath because we are diving into the final section of the technical calculation.
The math section.
This is where Satoshi rigorously proves mathematically that the system is secure against attack. The text poses the ultimate nightmare scenario for the network. What happens if an attacker tries to secretly generate an alternate chain faster than the honest chain to rewrite history?
Let's reiterate the boundaries of this attack first. The paper repeats that even if an attacker builds a faster chain, it does not throw the system open to arbitrary changes.
I can't do whatever they want.
They cannot create value out of thin air, and they cannot take money that never belonged to them because they cannot forge the digital signatures of honest nodes. The honest network simply won't accept an invalid transaction, no matter how long the chain is.
So the attacker is strictly limited to the double spend. They buy a digital good, wait for the merchant to deliver it, and then race to broadcast a longer, secret chain that erases their payment, keeping both the good and the money.
It is entirely a race, and the paper characterizes this mathematical race using concepts from probability theory. It calls it a binomial random walk, and specifically frames it as a gambler's ruin problem.
Let's break those terms down for the listener. What is a binomial random walk?
Imagine walking a tightrope where you take steps of equal length, but the direction is random. A binomial random walk means there are only two possible outcomes at any given step. You either step forward or you step backward.
Okay.
In the context of the white paper, the success event is the honest network finding the next block and extending its lead over the attacker by one block. The failure event is the attacker finding a block and reducing the honest network's lead by one block.
And a gambler's ruin problem.
The text explains it beautifully using a casino analogy. Suppose a gambler with absolutely unlimited credit starts at a deficit. They sit down at a table where the odds are against them, and they play potentially an infinite number of hands to try to reach break even.
So they're playing from behind.
What is the mathematical probability that the gambler ever reaches break even? In our blockchain scenario, the attacker is that gambler. They are starting at a deficit because the honest chain already published the transaction and moved ahead, and we want to know the exact probability that the attacker can ever catch up and overtake the honest chain.
To solve this, the text lays out three specific variables, puate and tugals. Let's define them.
Sure.
Poodle is the probability that an honest node finds the next block. Codal is the probability the attacker finds the next block. And needle is the number of blocks the attacker is currently behind.
And the fundamental required assumption of the entire system is that Poodle is strictly greater than Tooler. The honest nodes, collectively, must have more CPU power than the attacker.
The house has the edge.
Because Poodle's is greater than $2, the house has the edge.
Yeah.
The paper states that the probability of the attacker ever catching up drops exponentially as ZLers the number of blocks they have to catch up increases.
The paper includes a great quote here. With the odds against him, if he doesn't make a lucky lunge forward early on, his chances become vanishingly small as he falls further behind.
It's a great line.
It's like playing roulette against a casino. You might win the first spin by pure luck, but the longer you play, the mathematical certainty of the house edge grinds you down. Your chance of coming out ahead approaches absolute zero.
But Satoshi doesn't stop at theoretical generalities. The paper shifts perspective to the merchant waiting to receive a payment. The core question for commerce is, how long does the recipient of a transaction need to wait before being sufficiently certain the sender can't reverse it?
To calculate this, the paper models the attacker's potential progress using a Poisson distribution.
Right. A Poisson distribution is a probability model used to predict the number of discrete events occurring in a fixed interval of time or space. For example, predicting how many meteors will hit the Earth in a given year based on the known historical average.
So how does that apply to the attacker?
We assume the honest blocks take an average expected amount of time to be found. During that time interval, the dishonest sender is working entirely in secret on their parallel chain.
Because they haven't broadcast it yet.
The merchant waits until the transaction is added to a block, and then waits for a specific number of subsequent blocks, Sybilers, to be linked after it. The merchant doesn't know exactly how much progress the attacker has made in secret during that time.
Right, it's a mystery.
But using the Poisson distribution, they can calculate the expected value of the attacker's progress based on their known share of network power. The text gives the formula for the expected value, lambda, equals 0 times $, divided by time.
And then, amazingly, Satoshi actually drops an algorithm written in C code, literal programming code, right in the middle of an academic white paper to calculate the exact probability of the attacker succeeding from any given point.
It's a flex, honestly.
And the results they print out are absolutely staggering. I want to walk through the concrete examples from the text because this is where the theoretical math becomes an impenetrable shield.
Let's run the numbers from the paper.
Okay. Imagine the attacker controls a substantial 10% of the entire global network's computing power. So 2 call equals more 1, 1.
That's a lot of power.
You are the merchant. You see the transaction in a block, and you decide to wait for just 5 more blocks to be added on top of it. So CO equals 5. According to the Poisson distribution results printed in the paper, the probability of the attacker successfully rewriting those 5 blocks and stealing their money back drops to 0.0009137.
Less than 1/10 of 1%.
A 0.09% chance of success.
And the paper runs the calculation for an even more powerful adversary. Look at the table for an attacker with a massive 30% of the total network power, car equal equals 0.3.
That is a terrifying amount of centralized hashing power.
Yet, even with that huge chunk of power, if the merchant simply waits for 20 blocks equals 23, the attacker's success rate is mathematically calculated at 0.00248804. It is practically zero.
The final table in the paper provides a quick reference guide. It solves for a probability of less than 0.1%. It shows that if the attacker has 10% of the power, you only need to wait 5 blocks to be perfectly safe.
And if they have 30%?
If they have 30% of the power, you just wait 24 blocks. The math is relentless and undeniable. The longer you wait, the more computationally impossible the attack becomes.
This mathematical proof raises an incredibly profound point about the nature of this entire system. The introduction of the paper talked extensively about moving away from trust.
Right.
But the reality is you are still trusting something. You just aren't trusting a human bank manager or a central authority or a corporate referee anymore. You are trusting exponential mathematical decay.
Trusting the math.
The network is secure not because people are inherently good or because a corporation is well regulated, but because of the sheer probabilistic impossibility of an attacker sustaining a lucky streak against the combined CPU power of honest nodes over time. The math itself forms an impenetrable physical wall.
Which brings us to the conclusion of the paper and the synthesis of everything we've explored today in this deep dive. Reading through this text, it's clear Satoshi Nakamoto didn't just invent digital money out of thin air.
No, they stood on the shoulders of giants.
They took existing, disparate cryptographic concepts and fused them together. They took digital signatures for proving ownership, Adam-Back's hash cash for proving physical work, game theory for aligning economic incentives, and Poisson distributions for quantifying risk.
They mashed all these existing concepts into a single, breathtakingly elegant, decentralized consensus machine.
It remains a masterclass in systems engineering. The paper concludes by summarizing that the network is robust precisely in its unstructured simplicity. Nodes work all at once with very little coordination.
They don't need to be identified.
They simply vote on the validity of history using their CPU power. And any needed rules and incentives can be entirely enforced with this consensus mechanism.
For you, the listener, understanding this 9-page paper is a profound shortcut to being truly well-informed about the digital world. You now know that underneath all the modern noise, the volatile prices, the regulatory debates, and the media headlines, the core engine of this revolution is simply a global network of computers blindly guessing random numbers, burning physical electricity to lock in a cryptographically sealed, time-stamped history.
It strips away all the magic and leaves you with the raw mechanics. But before we sign off, I want to leave you with a final provocative thought.
Let's hear it.
Something derived entirely from the text we explored today, but something that points to a potential vulnerability in the distant future. We talked deeply about the incentive structure.
Right, the rewards.
The white paper states that once a predetermined number of coins enter circulation, the block reward ends, and the incentive transitions entirely to transaction fees. It's designed as a self-sustaining closed loop. But I want you to think about this. When there are no more new coins to mine, and miners must rely only on the fees attached to transactions to pay for their massive electricity bills, will those fees be enough of a carrot to keep that massive global CPU power running?
That's the big question.
If the fees aren't high enough to cover costs, honest nodes will turn their machines off. And if the total honest CPU power drops, the math of the gambler's ruin inherently shifts. That impenetrable wall of probability we just talked about, it gets lower, the house edge shrinks. Suddenly, the idea of an attacker catching up doesn't seem quite so impossible.
It's a fascinating economic vulnerability built right into the long-term mathematical design of the system, something to mull over.
A very compelling question to ponder as we look to the future of the consensus mechanism described in these 9 pages. Thank you for walking through this fascinating document with me.
Thanks for having me. It was a great conversation.
And a huge thank you to you, the listener, for joining us on this deep dive into the code. Until next time, keep questioning how the invisible machinery around you really works. Catch you later.